So in the previous video, what we did is we started with a distillation column with 13 stages, a reboiler, a condenser, where we are feeding into stage 7 with a set relative volatility, feed rate, mole fraction of the more volatile component, a liquid mole fraction, and a reflux ratio. And based on all of that, we used the concept of the molar holdup to give us these plots. This is a plot for the molar holdup, the total amount of moles per stage as a function of time. And this is our mole fraction of the more volatile component over time. And after that, we also developed a McCabe-Thiele diagram that gave us the steps that correlate with the design of our distillation column. Today, what we're going to do is we're going to delve into more of the relationship between the reflux ratio and the molar holdup within a distillation column. And the way we're going to do that is we are going to set a ramped function that will ramp up from a reflux ratio of 2 to a reflux ratio of 4 over a 130-second time span ranging from 20 seconds to 150 seconds. And we will generate McCabe-Thiele diagrams to analyze that change in time. So what we're going to set up first is I'm going to set up a function called ramp factory, and I'm going to give it a few inputs. So the inputs are going to be y1, y2, x1, and x2. So what each of these things stand for. So y1 is going to be our initial state, and that initial state is going to be our initial reflux ratio, which is 2. Y2 is going to be our final reflux ratio that we want to settle upon when we hit our final time. X1 is going to be the initial time where we start the ramp up, and X2 is going to be the time where we end the ramp up. So Y1 and X1 are a pair, Y2 and X2 are a pair. We are just going to use a slope-intercept form to give us a ramp up from 2 to 4 over a set period of time. Kind of like linearly spacing, but in this case, we're going across a set range. So we'll start off by defining our ramp function that's going to take an input of t. And essentially what we're going to be doing is we're going to be setting up a few conditionals. So we'll say if t is less than x1, throw my if statement. So if t is less than x1, we just want to return y1. If we are less than the time we have specified where we want the change to happen, we're just going to give the value before the change. Simple enough. We're going to give it a second condition saying that if x is greater than x2, then we have reached our steady state and we are going to return our y2. If we don't meet either of those conditions, that means that we are falling between the range of x1 and x2, and we are going to return basically the slope-intercept form of what we are doing here. So initially we are starting at y1, and we are going to add, so this is our slope, y2 minus y1 over x2 minus x1. I'm going to put these in their own parentheses. And then multiply it by our x, our change in time. So that's going to be the time that we're at minus our initial time. So this is the time difference, and that'll give us the point along the slope upon which we have fallen at that given t. Then we're just going to return our ramp function, and that should be about it for our ramp factory function. So just to check if this works, let's just quickly plot out what we have done here. So I'm going to set up a set of times that we want to plot over. So np.lin space, we'll go from, we need to be, so let's start at 0 and then we'll go, let's say 300 seconds because we're going from 20 to 150. So that should work out fine. And let's say we want 500 evenly spaced points. So let me go ahead and store the result of this function into a new variable called rramp. And this is going to be our ramp factory function with our given input. So y1 is going to be our initial R, and then we're going to go to 4, which is the final reflux ratio upon which we want to settle. We will start this change at 20 seconds and then end this change at 150 seconds. So now that should have stored in there. However, if we actually look at what the output of this is, we're not really going to get anything of interest because we don't have a time range yet. So once we plot it out, it will be a lot nicer to look at. Now what I'm going to do is I'm going to open up a new array, an empty array for our R's. And I'm going to say for t in tplot, I'm going to calculate a value and I'm going to append it to my empty array. So I'm going to append my rramp as a function of t. So now what I can do is I'm going to make a new subplot. Add a scatter. That seems to be all right. So let's just take a look. And there we go. We see that at 20 seconds, we start ramping up slowly to our final reflux ratio of 4, and we stay consistent with that until the specified time. So that's just a good way to ensure that what we have done is correct. And now the next step will be incorporating this into generating a handful of McCabe-Thiele plots. So what I'm going to do down here is I'm going to go up and I'm going to grab this right-hand side function that we had earlier. I'm going to copy and paste it back down here. And this time we're going to do this for a ramped reflux ratio. All right. Okay, well, the issue with doing this is if we look up here, in our vapor flow rates, we have a dependence of R going all the way down into the array that we created for our molar flow rate. So all this has to come down here. And what we're going to do is we're going to say that R is equal to our R ramp as a function of time. And that R ramp comes from here. So now whenever we go and do our ramped R analysis here, it'll go through the function that we had coded earlier, ramping up from 2 to 4 over this time span. And then we can actually use the solution from this. So let's go ahead. So we're going to use our solve IVP. This time we're going to be solving our ramped R. So go from 0 to t end. Our initial guess stays, actually, our initial guess is going to come from here, this result right there. I'm going to set the method equal to redaw. Set dense output equal to true. It seems to have converged. So let's take a look at the solution. So we have our time spans, we have our y values upon which it decided to integrate. So we can now use this information and generate some McCabe-Thiele plots. So I think I forgot to hit shift enter somewhere and I was getting pretty different results to what I have here. But what I have right here are the correct results. That should come as a result of this change that we have here. So let's go ahead and I'm going to I'm going to take my result here and I'm going to plot it over a solution time frame. So I'll call this tsol equals, I'm going to do a linspace, so 0 tn, which is 200 seconds. And let's say we want 6 time intervals for 6 McCabe-Thiele diagrams. So let's take a look at this. So what we have here is we have our mole fractions, and then at some point along the way we get our total number of moles. So what we want to do is we want to split this into 2 along the axis equals 0, like we had done before. And just double checking, yep, it seems like we have the moles in one array and we have our mole fractions in the other. So first comes our mole fraction, so we'll say that this is our, what do we call this? X, I don't really know actually. X underscore? Underscore X? Why not? Underscore M. Yeah, that should work out. So now if I do this, I should be able to grab just my mole fractions here. It's perfect. So now what I'm going to do is I'm going to have to do a for loop. So I'm going to say for I in, let's say, I want to do this for the number of arrays that I have that in my mole fraction. So I could say something like underscore x dot shape, because that will give me the amount of values that I have. So if I actually went and did, so underscore x dot shape, if I want this value, the 6, which is the amount of time steps that I gave it, I have to put in a 1 here. So that will give me the correct amount of McCabe-Thiele diagrams according to the time steps that I had taken during my solution. So before I do the loop here, what I'll do is I'll set up a new bound of equilibrium x's, and that's gonna be pretty much copy paste from what I had up here. So yeah, why don't I just copy this? In fact, I'll just copy all this because I'm pretty sure I'm gonna need it. So if equals make subplots, sure. That looks good. That looks good too. So I'll get rid of that. Now, for this loop, I'm going to have to add each of these to each new McCabe-Thiele diagram. And when I set my x's, that's going to be the x's I grabbed from my solution, colon, so everything, and then just the I, so whatever time step that I'm looking at. So this is all of the fractions, and then this is just the I that relates to that set of mole fractions. The y's here is going to be similar to my equilibrium y's here. So I'm going to copy and then paste this over. In this case, it's going to be x's. All right. And then I need my McCabe x's. And in fact, these are going to be straight out of the McCabe-Thiele diagram we had done earlier. So something like that. Let's just see. So I forgot to set this equal to a range. So now if I do that and I force the figure to show, what I get is basically all of the McCabe-Thiele diagrams on one chart, which is not what you want. That's not helpful to see at all. So in order for us to be able to see all of them, what I'm going to do is I'll set my rows equal to 1. And I'll set my columns, equal to the shape of X. All right. And now, every single time we loop this, I want to add the diagram to the next column over. So I can use the counter built in to my... I can use the counter built in to take all of kind of the overlaps of this graph and put them all out in front of me. So in this one, we'll say so row is equal to 1, call is equal to my I plus 1. And that goes ahead and puts my equilibrium curve on separate things. So I'll copy and paste this for the rest of my lines. And there's a lot of color mismatch here, so I'll go ahead and I'll set these line colors. Say we want our equilibrium to be blue. We want our x equals y equal to gray. Is it line color? So the proper line attribute is the line color. So now if we hit Shift Enter on this, we have generated now 6 McCabe-Thiele diagrams for the 6 time steps that we have specified in our solution. And as we see, with each increasing time interval, which means that our reflux ratio is going up, we see that we actually get better separation. Over here, if we look at this very top line, we see that our distillate composition is about 0.92. And as we go on, we get up to about 0.93 and so on and so forth. So increasing that reflux ratio actually leads to a better separation overall. We also take bigger steps in between each one of our stages. You see that as we approach this intersection with the Q line and the equilibrium curve, there's a bit of a pinch. So there's a bit more waste going on over here, but that sort of evens out as we increase the reflux ratio. So that's just a quick little analysis on how ramping up the reflux ratio can affect the quality of the separation and the compositions at each end. And yeah, pretty cool.